Okay, this is lecture 4, Physics 112, and today we are going to talk about chapter 18. So we are going to talk about electrostatics and forces between static electric charges, and also we'll talk about electric fields and so on. So we know that there are two types of charges. One is called positive charge. I'll write plus VE for positive, that's a shorthand. For negative charges, minus VE for negative. And experimental facts have shown us that like charges, like positive and positive, they will repel each other. Similarly, negative and negative charges, they will repel each other. And unlike charges, let's say plus and minus, will attract each other. So we say that like charges repel, unlike charges attract. Okay, don't forget that. Now, when we talk about charges, then we wonder how we get these charges. Actually, they are elementary unit of charges in nature. The first elementary charge that we found was called electronic charge. Actually, it comes from a little particle called electron, which is one of the most fundamental particles. And the electron, it has charge Q sub E, and we call the electronic charge to be negative charge. All right, so the magnitude of this electronic charge Q sub E is 1.6 times 10 to the power minus 19 Coulomb. Coulomb is the name of the guy who studied electricity. C-O-U-L-O-M-B, Coulomb. Okay, that's the unit for charge. Now, how do we get into these elementary particles? Well, every object can be subdivided into subunits. And so let's look at our hand, for example. The hand will have cells. So let's look at the cell. Of course, I'll draw just a little cube. So it's not really a cell, but just a cartoon form of a cell. Then in the cell, there are other subunits, but if you go down deep enough, you will find what we call molecules, right? Molecules are just some atoms bind together, and these are molecules. And each molecule is made out of what we call atoms. And the atoms has two basic parts. One is called the nucleus, which has positive charge, and it is in the center. And electrons are going around this nucleus in orbit. So these are negative electrons going around in some orbits. Okay, so I'll draw only two. So actually, all the positive charges, the amount of positive charge and the amount of negative charge in general are the same, so that atoms are basically neutral, so that you will not get electrocuted all the time. But of course, you can remove some of the positive charges or some of the electronic charges, then you will have, let's say, like for example, some ionized atom, right? But we are not going to talk about that right now. So inside the nucleus, there are two types of particles. Actually, there are more, but in general, basically, there are two types. One is called proton, and one is called neutron. So I'm just writing N and P. I'm not writing them in any particular order. And this will be a nucleus. And the neutrons they don't have any charge. Q neutron is equal to 0. Charge of a proton, Q proton, has the same amount as electronic charge. So the amount of charge that a proton has is the same as the amount of charge a neutron has. Okay, this proton. Now, the reason that proton has a positive charge is a little bit complicated, but I'll try to explain to you. Protons are not as fundamental as like electrons. Electrons are point particles. You cannot subdivide them. But proton is made out of 3 what we call quarks. U, and a D. Quarks are considered to be fundamental and you cannot subdivide them. But a U quark has positive 2/3 charge, that is 2/3 of electronic charge, and a D quark has negative 1/3 of electronic charge. So when you add them up for U, and a D, U, and a D, you will get 2/3 for the first U, 2/3 of QE, and another 2/3 of QE for the second U quark, and negative 1/3 for the down quark. See, U is called the up quark and D is called the down quark. If you add them up, you'll get 1 unit of electronic charge, but positive. So the proton's charge is positive. For neutrons, the structure is different. The neutron has D, and a U. That's for neutron. Sorry. So U, a D, and a U, that's for neutron. And if you add them up, D has negative 1/3 of QE, and another D has negative 1/3 of QE, plus 2/3 of QE for the U. So if you add them up, the net charge is 0 for neutron. Okay? All right. Now, one thing you should know, just for general knowledge, is that these quarks we have never found them free quarks, right? They are not free. They are always inside protons or neutrons, all right? But we know that they are there because there are some experiments that tested that they found that they are inside these protons and neutrons, but you can never find these free quarks, all right? Let's go to next page. So now I have talked to you about like charges repel and unlike charges attract and so on. So this will be page 5 and physics 112. But I didn't tell you how much the force will be. So there's something called Coulombs Law, Coulombs, Coulombs Law. Coulombs Law tells you that the force, the magnitude of the force between two charges is proportional to the magnitude of the first charge times the magnitude of the second charge divided by their separation distance squared. Okay, that's proportionality sign here. So if I want to make it an equal sign, then I'll have to put a proportionality constant. So F is equal to the proportionality constant, we call it K, Q1 times Q2 divided by R squared. So this is known as Coulombs Law, right? So first we can calculate the magnitude, then after that we'll say what direction they will be acting depending on what type of charges they are. So the units are important in physics. Q charges Q, the unit will be in coulombs. And we'll just write C. And for distance, that will be in meters. We'll just write M. And for force, that will be in newtons. And we'll write N. So then from this equation, you can see that on this side there's Newton, on this side there's Coulomb and Coulomb, so that's Coulomb squared, and R squared is meter squared. So the unit for K will be Newton, because that's Newton, meter squared, so you will multiply by meter squared divided by Coulomb squared. So the constant K will have units Newton meter square per Coulomb square. Actually, there's a precise number that we have measured from experiment. K is equal to 8.89 times 10 to the power 9 Newton meter squared per Coulomb squared. Okay? Now, let's do an example of how to use this Coulombs law. So I'll start with the simplest example. So the simplest example that I can do is the magnitude of the force between two charges. Let's suppose they are positive charges. So I have, let's say, 0.05 Coulomb on this side is a positive charge. And then on here, then I'll have 0.0003 coulombs. I have a reason that I put all these zeros, so you will see in a second. The separation distance is, let's say, let's make it 4 meters. Okay, 4 meters. Quite far, 4 meters. All right. Now, let's calculate the magnitude of the force between these two charges. So we first write down Coulombs law. F magnitude is equal to K Q1 Q2 by R squared. Now we put the numbers. K is 8.89 times 10 to the power 9 Newton meter squared per Coulomb squared. Then for Q1 and Q2, Q1 is 0.05, so 0.05 Coulomb. Q2 is 0.0003 coulombs divided by 4 meters squared. Okay? So you see, there's Coulomb squared. So you see that there's Coulomb square will cancel out, meter square will cancel out. The only unit that will be left is N, that is the Newton. Alright? So I'm just trying to tell you what I'm doing with these numbers. I'm not going to plug in everything directly into calculator, right? Because that's how you get wrong answers, because sometimes you're rushing, or sometimes you're careless, sometimes you see it wrong, whatever. So before we do anything, let's write it down. So I'll write down 8.89. I'll leave this alone for a second. 0.05. What is 0.05? Let's write it in 10 to the power notation. So if I move 2 decimal places, that will be 5 times 10 to the power negative 2. Right? And then here I can move 1, 2, 3, 4. So that'll be 3 times 10 to the power negative 4. So you see 1, 2, 3, 4. 4 decimal places. Here I move only 2 decimal places. Oh, don't forget this 10 to the power 9. And divided by 4 squared is 16. Okay? So you see, if I do it that way, then I can plug in 8.89, 5, and 3 divided by 16 in the calculator, but I don't have to worry about these because I can just add them up. So let's do that. So before we do that, we can also see approximately how much it will be so that you can tell whether the number you get from calculator has no error. That means not that calculator is going to be wrong, but you'll be punching in wrong numbers. I know that. So let's see 5 and 16. 5 goes into 16, approximately 3 point something, right? Because 5 times 3 is 15. So it is approximately 3, and 3 cancel out. So that means the answer is about 8.89, right? Fine. So it'll be close to that. Right? So as long as we get that, it'll be fine. And what about these numbers? So that's 10 to the power negative 2, 10 to the power negative 4. So altogether 10 to the power negative 6. And with 10 to the power 9, it'll be 10 to the power positive 3. Because 9 and this is negative 6, so it'll be 3. So let's check. So 8.89 times 5 times 3 divided by 16 is equal to 8.33. See? So it's 8.33 times 10 to the power 3 newtons. Alright? So the magnitude of the force will be 8.33 times 10 to the power 3 newtons. Alright? So you see these numbers are close. Otherwise, I can tell something wrong, right? Because if I punch in something wrong, I'll get some crazy numbers, right? Okay. So I'll see you in next lecture.